is professor at ECA, which is from Grammars and of bicycling. So
thank you for inviting me. I'm sorry for the switching concerning the presentation. I have an issue. I need to leave at 1 o'clock. So I'm Olivier Français. In English, I used to say I'm Oliver French. It's more easy to understand for you, maybe. And I'm professor at the Université Gustave Eiffel. So. Yes, it's going. Okay, so we are on that square. So my university is between Disneyland and the Eiffel Tower. We are just at the middle. If you take RER A, you will find us at the middle. And I'm part of the lab ESICOM, which means it's dedicated to microsensor and communication micro devices. And we are lucky, in fact, because in our lab we have a wonderful clean room. And there is a delay between. We have a clean room on which we can fabricate a lot of micro devices, such as lab on chip with microfluidic parts. But we also have the technology to fabricate up to 6 inches wafer, meaning that we can have a lot of the micro devices on one single wafer. You have some example of application, lab on chip, multi-sensor platform. We have a specific technology around soft medical implant. I will make a short introduction on that. And we have linked with industrial partner. As you know, we focus on micro devices. So what I will present will focus on that typical size between millimeter size concerning the channel and the access, and up to micrometer size for cell handling within micro devices. So you have one typical example of a gradient generator, which is fabricated in our clean room, and we use that gradient generator in teaching part for in my school, because I'm a teacher in the engineer school. Okay. So we use silicon, glass, and polymer material to fabricate these devices. So one example, we own a European project labeled Neurodiam, which is dedicated to developing micro devices using diamond. So this is a diamond obtained in oven. We fabricate a soft diamond implant that can be used to record and to monitor neuron activities, for example. And you have some example of cells. It's muscular cells that grows on microelectrode array, and we can monitor electric activities of that typical cardiac cells, for example. And to conclude on what we are able to do, because I've seen some presentation using microtechnology, so maybe we can have some link after that if you need some specific technology and so on. You have one example of a multi-sensor platform, which is dedicated to water monitoring. On that multi-sensor platform, you have physical sensors with pressure, flow rate, temperature, and conductivity sensor. It's on that location. The chip is less than 1 centimeter square, and we have also chemical sensor that can monitor pH, concentration of chloride, nitrate, or also hardness of the water. So this is also a fund from a European project that gives us that opportunity to fabricate that chip that now it can be used with industrial partners. Okay, so today thematic is not that, but it's more focused on what we can say organ on a chip. I have seen some devices that mimic some organs. In fact, we have seen some blood flow in vessels. So you know there is liver chip, kidney chip, lung chip. Today I will discuss about how we can study blood flow in the cardiovascular system using microfluidic devices. There is several sizes. When you look on cardiovascular system, you have the artery of the vein, which size it's in centimeter size, which is you can use classical technology to fabricate that. And for us, we will more focus on capillaries, where the size associated to capillaries, where you have some exchange in the organs. Main exchange are connected to red blood cells when you have oxygen exchange and CO2 exchange. And you have typical size in diameter, which are from 2 up to 10 micrometers, where you will find blood flow. So we will focus on blood flow in that kind of capillaries. And in my lab, we study a well-known disease labeled as sickle cell disease, which is induced by genetic disorders. When you have a variation in oxygen concentration within your blood, you have some polymerization of your hemoglobin that change the shape of the red blood cells. It passes from, let's say, a donut shape toward a moon shape. That gives the name of the sickle cell disease. And it induces some vasoocclusion in your vessels that stop the blood flow, and that can induce defect, trouble in your organ. So we focus on that particular trouble, and we develop devices in order to mimic the pulmonary blood system. So if you look on the pulmonary blood system, you have capillaries that are located in the lung alveolus, where you have the gas exchanges. And if you focus on a cut view on that capillary bed where you have the gas exchange, so we are in that part of the pulmonary capillary bed, which achieves the link between arterial and venules. So you have the arterioles here, the venules here, and the link between both is the label capillary bed. And you can see it looks like what we have seen with bacteria. It's like a matrix when you can see microchannel and the red blood cells travel across the microchannel. So when you have a sickle cell disease, there is trouble that because red blood cells can be trapped and block the gas exchange, so you have trouble in your breast. So we focus on that shape, and we have this simple idea to reproduce that matrix using micro devices. So it's an hexagonal matrix with channel. If you look on the side on that capillary bed, you have channel with a typical size of 8 micrometer size, so it's easy to obtain using a molding technique with PDMS. So we start to simulate the behavior of that matrix, because we want to have a physiological condition having the same drop pressure between arterial and venule. So we design some initial cell with the specification of having 200 Pascal of drop pressure for, sorry, there is French part, for a local velocity of 1 millimeter per second. So it was the specification we have, so we designed that hexagonal shape, and we study, of course, the velocity flow and the drop pressure to have that specification, and we design the full devices in order to have a lot of experiments achieved in parallel. So you have the one capillary bed that we connect 8 times together to achieve multiple experiments at the same time. So the capillary bed is 8 micrometer for the thickness, and the axis, in order to have a less drop pressure, is 20 micrometer thick. So you can see the axis, the blood will pass through the capillary bed, and we can study effect in case of sickle cell injected. So here is the process. We have seen previous slide and seen from the previous speaker that explain the molding technique. So you have it's SU8 molding technique with the two thickness, 8 micrometer thickness for the capillary bed and 20 micrometer for the microfluidic access. So it's full PDMS device. with bonding on a glass slide using O2 plasma. And after we have the full process, but I think I can save time using that. So we discussed about lab on a chip, but in fact it's more a chip in a lab. We need more space compared to the chip. So you have the chip here. It's under microscope, and we can inject with syringe pump, but in fact we are using a pressure controller in order to respect the physiological condition. So it's not syringe pump, it's a pressure control in order to have the good pressure within the chip. So here is the results. So you can see the, so we have a medical partner. I'm more physicist compared to biology. So we did that with Henri Mondor Hospital. That is, there is a specific unit concerning sickle cell disease. So you can see the blood injection and the flow of the red blood cells across the capillary bed. In a normal condition, you cannot see some blocking part. So the issue for us, it was to study the velocity of the red blood cells and how, in case of vasoocclusion, the velocity flow of the red blood cells change. So to do that, we start to have some optical analysis. So you have a single first experiment with a low concentration of blood, and using image analysis, we were able to extract the velocity of each particles within the device. This was not so far compared to the previous talk. And from that results, so you can see we have a dynamic analysis of the moving of the cells. Each burrow represents one particle that has been detected, and monitoring the evolution of the position, you can extract the velocity and the direction. From that study, we extract the histogram, the statistical evolution of the velocity, and you have also tracking where the cells are passing through the device in an automatic way. In that situation, you can notice that some hexagonal locations are missing concerning the passage of red blood cells. It means you have a vasoocclusion and you have a redistribution of the velocity. So from that situation, we have two kinds of flow that have been studied. First is a normal flow, and the second one is a flow with red blood with sickle cell disease. So red blood cells having that typical pathologies. So you can see you have some location within our device that induce vasoocclusion. Of course, we have some. We validate that the occlusion of vessel is due to the pathology, and not due to the contact concerning the wall of the PDM chip. So from that, we have the statistical analysis of the flow. In normal flow, we have the typical Gaussian evolution, meaning you are in biology, you have statistical variation concerning the flow. And in case of sickle cell disease, you see we have a redistribution of the velocity, meaning that we have a disorders in our flow. And we can also notice we find two Gaussian law, and it can be associated to the fact that there is redistribution, but also to the fact there is two kinds of population within the blood: normal red blood cells and sickle cell red blood cells. Okay, so it's real-time visualization, and from that evolution we can extract the velocity and make some analysis if there is some vasoocclusion event. And starting also with that, we have some devices that study exactly what had been presented before, but we can do that in one single channel, but also we can do that in a parallel way. That result is coming from here. In fact, it was several years ago when I was there, we developed that kind of chip that helps to study evolution of blood flow within micro device. So now the next part of my talk will focus on one single microchannel in order to study the capability of one red blood cell to travel across one channel. So we have seen that red blood cells are very important in our life because it's oxygen transport. And if you see the evolution of one cells during one travel across our body, it can be squeezed, of course. You have that typical evolution. Every 20 seconds, one red blood cells is in average submitted to a squeezing effect. So depending on its deformability, it can travel fast or travel lower. We have seen some issue previously, or can block completely the cells. So we developed a way to monitor that traveling across the channel using electric field, meaning that from that traveling of one cells across a capillary channel, we would like to have an automatic analysis of the passage across the channel. So you can see starting from a donut shape. After it's typical, not so clear, but it's a bullet shape, and depending on the recovery of the initial shape, you can deduce some typical deformability of the red blood cells. For us, in case of sickle cell disease, there is huge disorders in that traveling. So the idea was to put some electrode at the starting and at the end of the channel to have an electrical monitoring of the passage. So we combine microfluidic with electric parts. So you can see it's not so clear, but we have a channel, and between the channel we put some electrode to monitor the passage across the channel. In that case, we did not use PDMS for the channel. We used SU8 in order to have good alignment between the electrode and the channel, because it's very complicated to put a microchannel at the micro size resolution compared to the electrodes. So the principle is very well known. It's a bioimpedance analyzer. It comes from the 60s, where with Professor Coulter that create the Coulter counter, which is a way to count cells across a hole, a small hole, by monitoring the drop of the current when the cell passes through the hole. You have two electrodes between the hole. You control the current. If one cell passes through the hole, you have a decreasing of the current, so you can have some analysis of that. So one issue was to choose a frequency, because if you want to monitor